I'm expecting Bill Cheb's new MOAT tube, that's the mother of all tubes, a 12-inch Phanotron, to arrive very soon. Been waiting for it, should be here any time now. There it is. Oh wait, no, that's not it. That's the wrong box. Go away. Ah, that's more like it. This is the box we're looking for from Bill Cheb. And you will notice that it says, do not stack. This box will not support heavy weights. And look at the edge of the box. It's been creased. They've stacked something on it, apparently a heavy weight. Anyway, we're going to open the tube box up and see just what it looks like. Okay, we're going to unbox the tube. Now, I'm going to cut one end of the box open. And I'm using the thick part of the box where it's doubled over, because when it's sealed up for reshipment, that will make it more sturdy. So when you're opening a box from Bill Cheb, you want to cut through 3 sides of the box. That's 1. That's 2. And 3. Now if you cut all the way through, which I didn't quite do here, you'll be able to open it. All right. Now we have a giant load of peanuts, plastic peanuts. And we have to get a lot of those out of the way so that we can get to the tube. So let's proceed to do that. I see glass. I see a lot of glass. There we are. Beautiful 12-inch diameter Phanotron. The next thing we'll be doing is taking measurements as far as physical dimensions. Then we'll go ahead and make a frame for it and do electrical tests. have it. We finally have a working tube stand assembled from 1-inch pine. So it's time to put the tube in the stand. See what it looks like. And there it is. I'm going to run some DC voltage tests on the tube. The first thing I'm going to do is set the firing voltage on the tube, which I've already determined is 1700 volts. So here's what the tube looks like with 1700 volts DC applied when the electrodes are just starting to light. At this point, the tube is drawing about 2 milliamperes. The running voltage is considerably lower than 1700 volts. Let's take a look at the electrode here. You can see that the discharge is running around the electrodes. It's not a steady glow. If we increase the current, the discharge will become more solid and start to cover more area on the tube. We're running the tube at 10 milliamperes DC. The right-hand electrode is the negative electrode, and the left-hand electrode is the positive electrode. If we reverse the direction of current so that the left-hand electrode is negative and the right hand is positive, it looks like this. And if we decrease the current, you can see the glow on the negative electrode where the electrons are being emitted becomes smaller and smaller as we reduce the current. Finally, when the current is low enough, the tube will go out. There, tube is going out. It's trying to light, but there's not quite enough current capability to be able to keep it running. So anyway, here's an interesting effect you see when the current is about 1.5 milliamperes. You get a really crazy looking display on the negative electrode. Here is the Phanotron in the test setup. In this arrangement we have an LC31L BAT coupler, which turned out to be the one that worked very well with the tube. The tube matches the amplifier quite well and the system is capable of high power. You will also see on the coaxial cable here 2 mixed 31 ferrite toroids which keep RF from flowing back through the cable. There's quite a bit of RF field around the tube and the wiring, and this is due to the fact that this Phanotron requires a very high voltage to fire it. I'll demonstrate that a little further on in the video. We'll start applying RF power to the plasma tube. Nothing happens until we get to a voltage of approximately 76 volts. At this point, you can see there's a glow around the electrodes. We're starting to ionize the gas, but the tube is not in full conduction. At 95 volts, the glow gets considerably brighter, but the tube is still not being fully ionized. At 114 volts, the tube goes into reasonable conduction. At this point, the tube is seeing about 240 watts peak power. As we raise the power level, the intensity of the glow gets higher. As we raise it again, it's stronger, 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 and stronger still. At this point, the tube is operating at the maximum power level of about 581 watts peak power going into the tube. With all the room lights on, we can get a better idea of the intensity of the glow in the tube. There's a 76 volts, and you can just barely see the glow discharge. 95 volts, a little brighter. 114, there's a steady glow. 133 volts, 152, 171, 190 volts. That's full power into the tube. So you can see that there's quite a difference in brightness, which was not apparent when we had all the lights off in the room. There is a substantial RF electric field surrounding the tube and the coupler. When I move this fluorescent tube near the system, the tube will light. There's quite a bit of stray power in the vicinity of the tube. It's most intense in the area between the tube and the coupler. For this reason, if the system is used in an apartment or some area that is close to sensitive electronic equipment, it might be a good idea to put a metal shield, screen metal shield, such as a homemade Faraday cage, surrounding the tube and the coupler to prevent possible interference. It is recommended to install 2 RF choking toroids of type Mix 31 on the coaxial cable about 6 inches away from the coupler. This will prevent induced RF currents from flowing down the coaxial cable and acting as an antenna to radiate interference to other equipment. Although it's not absolutely necessary, it is strongly recommended since this tube runs at a very high power level. It's important to pay attention to how much power you send to the tube. If you use too much power, you can overheat the glass to metal seal of the tube and damage it. Observe the glow on the back of the electrode. As power is increased, the entire electrode will be covered with a glow. As power increases further, the glow will spread up along the metal support rod going toward the glass of the tube. When the glow reaches the glass, that is the most power you should apply to the Phanotron. Applying more power will cause excessive heating of the glass to metal seal and may melt the glass or crack it, resulting in a ruined tube. Here are some RF waveforms. These are taken in the amplifier tank circuit of the SPA5 amplifier. The plasma tube is connected to the output of the amplifier. This first waveform shows a voltage of 95 volts being applied to the amplifier. This is not sufficient to light the plasma tube properly, and you will note that the output waveform pulses are triangular in shape and sloped to the right. This indicates that the amplifier is not happy with the load, the tube is not fully in conduction, and this voltage will not be sufficient to operate the plasma tube properly. The voltage must be increased. The second waveform shows the amplifier waveform at 114 volts. You can see that the top of the waveform is rounded off. This is the correct shape that the wave should have. This next waveform shows the amplifier operating at 133 volts. The amplitude of the waveform has gotten larger, indicating more power to the tube. This next picture is 152 volts to the amplifier tank circuit. That is the optimum voltage where the amplifier is the most properly loaded by the plasma tube. However, higher voltages may be used for more power. Note the shape of the waveform with the slight downward jag about halfway down the right-hand side of the waveform. This is correct for the amplifier. This next waveform shows a voltage raised to 171 volts. The amplitude of the output waveform has become larger, but the wave shape is consistent with proper operation. This image shows the amplifier operating at its maximum voltage at full power and high voltage of 190 volts. At this point, the tube is running at maximum power and the amplifier is very happy. Now let's look at some waveforms showing the envelope of the modulated RF pulse. Here the RF carrier is being modulated by a 5 kHz square wave. Notice that the top of the modulation pulse is relatively flat and we have a clean rising and falling edge on the pulse. The two sharper pulses of slightly increased amplitude at the beginning of the modulation cycle is where the tube is just in the process of firing. This is the type of waveform that we want to see for optimum operation. Raising the modulation frequency to 50 kHz, we see the individual RF pulses in the modulation cycle. Note that they are all approximately the same amplitude with a clean pulse going into and coming out of the modulation series. Let's raise the modulation frequency again. Here we have 100 kHz. Notice that the pulse is shorter because there are fewer cycles in the modulation pulse. Again, entry and exit from the pulse modulation is good. This is producing a very good waveform output from the tube. Now let's go to an even higher frequency, 250 kHz, modulated at a 50% duty cycle. Here we see only a few RF cycles in each individual pulse. However, the tube is coming up to full brightness with each pulse and everything is working the way it should. This is the type of output that you should see from an amplifier when it's operating properly loaded into a good plasma tube. This is a thermal camera image of the plasma tube after it has warmed up for about 30 minutes. You can see the hotter parts of the tube indicated in white and the cooler parts in red, yellow, or blue. Notice that the coupler is below the tube and you can see it is also hot, but nowhere near as warm as the tube. This is normal. A closer look at the coupler shows that the ends of the coupler are the warmest, and you can see the individual turns of the primary winding where they are overlaid over the secondary winding. At this point, the coupler is operating at approximately 50 degrees Celsius. This is another picture of the plasma tube showing the warmest areas are in the neck of the tube where the electrodes are located. The electrodes radiate thermal energy, which heats the glass, which again re-radiates the thermal energy, and the tube shows up as this interesting color pattern in the thermal camera. Looking at one end of the tube, we can see that the glass has been heated considerably by radiation and the rising hot gas in the tube heating the top of the tube. The electrodes dissipate a considerable amount of power during normal operation, so that heats the glass to a temperature of about 84 Celsius.